Good morning or good afternoon, whichever one it is. I'm gone today, and so I'm going to record a short video, and hopefully that helps you along with your homework as well as getting ready for the lab coming up. So if all went according to plan, you should have already taken a quiz. And then right now, you might need to pause the video here in a second, but let's make sure we get everything out. You're going to need your redox notes, which are pink, as well as, let's see here, pink redox notes. We're going to finish those up. We're going to review homework 2, and I believe homework 2 is what? Green. So grab that green homework 2. We're also going to do an example on homework 3, which is yellow. That's a new one. And I just want to draw your attention to the fact that there's a reading on the great oxidation event on planet Earth that is blue. There's a reading and some questions as well. We're not going to talk about that in the video. We're just going to talk about redox stuff, but please get the oxidation event reading and questions done before next class. So quick reminder, right now I'm recording this on the 10th. So a little over a week from now, your product lists are due. Those hard copy pink pink cardstock product lists are due. Period 5 on 1/18 and period 4 on 1/19. If you have any questions about those, please talk to me or email me. First things first, let's get to the notes real quick and finish up a couple of things. So let's see, we talked about last time redox reactions, so oxidation reduction reactions, and that there's a few different ways we can look at oxidation and reduction. It kind of boils down to whether or not we are gaining bonds to oxygen, losing hydrogens, or losing electrons. That's what we call oxidation, or just the reverse of that, reduction, the loss of oxygen, the gain of a bond to hydrogen, or the gain of electrons. This is a handy reference. You might want to pause the video and jot that down. Just a quick bit of side note. So we looked at oxidation in systems where we're just looking at following the bouncing electrons. For example, ions forming, cations or anions forming. Anything that involves a gain of electrons, a gain of a negative electron is what we call reduction. Anything that involves the loss of an electron is what we call oxidation. We also looked at redox reactions in the addition or removal of hydrogen, so dehydrogenation reactions. In the forward direction of these equilibrium reactions, those are oxidations because they involve a loss of hydrogen. Hydrogenation reactions are just the reverse of that, the addition of hydrogens, the gain of hydrogen, those would be reductions. So we've talked about redox reactions in terms of electrons, we've talked about redox reactions in terms of hydrogens. We also talked about redox reactions in terms of gain or loss of bonds to oxygen. And this series right here is pretty important. This is like the simplest series of redox reactions where we take something like methane, add a bond to oxygen to form methanol, add another bond to oxygen to form the aldehyde, methanal, add another bond to oxygen to form a carboxylic acid. We haven't learned how to name the carboxylic acids for right now. We're just calling them organic acids. That would form methanoic acid. And then finally, the full oxidized form of carbon dioxide. Can't get any more oxidized than that. We're going to come back to this part right here shortly, but let's skip ahead to the next page. This patterns of reactivity is pretty important, and if you didn't understand this part or didn't write this down, then the homework would have been like pretty challenging. But the overall idea is that some chemicals or some functional groups oxidize fairly easily without a bunch of heat or changing the acidity or anything like that. Primary alcohols form aldehydes. Aldehydes in turn oxidize to form carboxylic acids. And then secondary alcohols oxidize to form ketones. And then we have a few different things like ketones, tertiary alcohols, and aromatic aldehydes that do not oxidize very easily. That table is pretty darn important. So maybe have that as a reference as we're talking about the homework. We did go into why this is the case, and it all has to do with whether or not there is a second hydrogen available for removal. That's kind of more like the mechanism stuff. But for now, it's enough to just kind of keep track of that table of information. So let's move over to the homework now. On the back page, I'm not going to talk much about the front page. You didn't have to do number 3. You didn't have to do number 5, although we'll talk about those things here shortly. Let's flip over to the back of the green assignment, number 6. We'll start with that. So this is kind of a little bit of backwards thinking here. So it's asking you to name and draw the structure of the alcohol that must be oxidized to produce the following products. What are the products? If it were me, I would take this shorthand version and I would draw it out. And if you draw that out, Lewis structure, you see that that is an aldehyde. What types of alcohols oxidize to form aldehydes? Well, primary alcohols. In this case, it's not really, I mean, it's like a zeroth alcohol because that carbon attached to the oxygen right here is not actually bonded to any other carbons, but we're just going to call that a primary alcohol anyway. These are like the simplest cases here. So we have an aldehyde. What would form this kind of aldehyde, this methanol? Methanol. That's the only alcohol that could oxidize to form aldehyde directly. Let's look at another one. What would form this carbonyl product? That is 2-propanone. That is a ketone. Ketones are oxidized from secondary alcohols. In this case, the secondary alcohol, again, that carbon right there is bonded to 2 other carbons, so it's a secondary alcohol. That secondary alcohol that would form 2-propanone has to be 2-propanol, because that's where all the magic happens, at that second carbon, at that secondary carbon. And that's kind of like the same pattern that we're going to see over and over, but the molecules are just going to get a little bit more complicated. You just have to kind of keep track of the R group. So if you draw out this structure on C, you end up with 2-methylpropanol. That's an aldehyde right here. We've got the carbonyl group with the hydrogen sticking off there, so that's an aldehyde. What oxidizes to form aldehydes? Primary alcohols. What primary alcohol is going to oxidize to form 2-methylpropanol? 2-methylpropanol, a primary alcohol. How do we know it's a primary alcohol? Because that carbon right there is only bonded to 1 other carbon. Variation on that same theme, again, going back to that pattern of reactivity. We have a ketone here, 2-methylcyclopentanone. Ketones get oxidized from secondary alcohols. What secondary alcohol? Well, it's going to be the exact same structure, but with a hydroxy instead of a ketone. I mean, that's another way to look at it. All right, let's see. Again, draw out the structures and then kind of backwards engineer the alcohol from whence it came using that pattern of reactivity. And again, feel free to pause the video at any time if I'm going too fast here. 3-pentanone from 3-pentanol. And then 7 is saying, okay, so using these same patterns of reactivity, what are the expected oxidation products? So in this case, you're given the reactants, what are the products going to be? So, and then when it says draw all the steps, what we're saying here is if you can get to the aldehyde and can go further to the organic acid or the carboxylic acid, then go further. For example, if we start off with a primary alcohol, what is that, butanol? First oxidation step would get you to the aldehyde, butanal. Second oxidation step will get you to it's called butanoic acid. Butanoic acid. For now, you don't need to know. I mean, you can probably figure out how to name these organic acids using IUPAC just from that alone. But right now, you can just call them an organic acid. B is a little bit of a trick question. It's our first tertiary alcohol. And again, those don't oxidize easily, so that's not going to have any oxidation products. This secondary alcohol right here, again, you draw that structure out. This carbon right here is bonded to one other carbon, two other carbons. So it's a secondary alcohol. Secondary alcohols oxidize to form ketones. Where's that oxygen, extra bond to oxygen? Right there on that second carbon, this carbon right here. That's going to form 2-butanone. So again, draw out the structure. It might be a little bit confusing because it says CH3 and then the carbon, but if you draw out that structure, you're going to get 2-butanol, secondary alcohol that oxidizes to form 2-butanone. Here is a secondary alcohol as shown. It will oxidize to form a ketone, same as the example that we saw before. And then, yeah, I mean, I feel like I'm kind of repeating myself at this point. So I'm just going to leave that up there. Primary alcohols oxidize to form aldehydes. Aldehydes can oxidize further to form carboxylic acids. Tertiary alcohols do not easily oxidize. So pause as needed, and then we're going to move on. Let's look at the next homework. I want to show you something real quick. So this next homework is homework number 3. It's yellow, and I want to show you kind of what I'm looking for here. Let's see here. So on the second page here. I'm sorry, on the first page, but the second problem. Grab my notes real quick. Okay. It says, draw both of the products that result from the reaction of 1 mole of aldehyde or ketone with 2 moles of alcohol. So this whole next set of problems is really more just practice using these patterns of reactivity and redox reactions. So I'm gonna go with a little bit of extra explanation on this one. So here is our carbonyl containing compound. This is a ketone, ethyl methyl ketone. And that is, the structure of that is going to look like, let's see, we got our ethyl, there we go. So so that would be 2-butanone in IUPAC world, but that's ethyl methyl ketone. So on the left, whoa, getting a little weird. Here's our ethyl group right here. And then here's our methyl group. Ethyl methyl ketone. I'm going to back those off because I want to keep this a little bit more clear and easy to look at here in a second. Okay, and 1 mole of aldehyde, I'm going to draw this in a different color. I'm sorry, 1 mole of alcohol. In this case, it is 2-butanol. So we've got something that looks like this, 2, 3, 4, and then 2-butanol. All right, so what is going to form here? The first step that's going to happen, so this is an addition reaction, an addition of an alcohol to an aldehyde or ketone. And I said earlier that these are redox reactions. This isn't technically a redox reaction for reasons that we'll talk about later. But in any event, here we go. So we did talk about these. These form the hemiacetals and the acetals and the hemiketals and the ketals. In this case, we're starting with a ketone. So the first thing we're going to do is form a hemiketal, 1 equivalent of alcohol added. And then let's draw this down here. That's our original oxygen right there that forms the alcohol group. Remember, a hemiketal will have an alcohol and an ether. So hopefully the color coding here helps things out. So here's where our ether is formed. And remember that oxygen has to be on that second carbon right there. And so if it helps anything, I'm going to draw this. It kind of ends up looking like, I'm going to say like a lobster with an oven mitt. That's what these end up kind of looking like. So there's our hemiketal, 1 ether, 1 alcohol, and then 2 carbons attached to that carbon that was once part of the carbonyl carbon. And then if it helps any, let's go back to the other color. If it helps any, we can kind of color code this as well. So that's our first, that's if we react 1 mole of ketone with 1 mole of alcohol. But let's go one step further because it says 2 moles of alcohol. So we're going to keep these carbons as is. And then here's our ether that was already formed. Remember that second carbon needs to be the one that's in the ether. We'll draw our oven mitt on the scorpion. And then we're adding one more equivalent of alcohol. And so if you did this part of the model lab, then hopefully this is making some sense. So we got to draw that second ether. And remember that second carbon will be the one that is attached to the oxygen. And if we do this, it ends up really looking like a lobster with oven mitts. And then what we end up with is H2O. That was the other product. So if you did that model lab, then you saw that water was formed as well. So this is the full ketal. So that's what I'm looking for on those. So that's a good representation of these particular addition problems. So, and then just the R groups are really the only things that change from there. So let's see here. I have one more thing I wanted to talk about on the notes, and hopefully this isn't too esoteric. In one class we skipped, I think it was period 5, we skipped oxidizing and reducing agents. We'll go ahead and keep skipping that for now. That's really fun. We'll come back to that later. But to finish number 3 on your homework, I wanted to talk about this, and I'll try to break it down as simply as I can for the purposes of this video here. But when we're talking about like what makes a reaction happen, we've really just talked about reactants form products, but we haven't really talked about why they form products. So there's a couple different considerations. One is enthalpy, which is what we're going to be talking about right now, kind of like the energy of the reactants, the energy of the products. Another is entropy, or measure of disorder. And we're not going to be talking about that at all. But if you've taken AP Bio, or maybe even touched on this in bio, entropy is an important consideration. But that's neither here nor there for this. What I want to talk about is something like a combustion reaction. Let's say we have methane like we looked at before. And I'm not going to balance this equation, but all combustion reactions involve a hydrocarbon plus oxygen forming carbon dioxide and water. And I mean, if you've ever like looked at fire before, you've seen the light energy, you have felt the heat energy. Energy is liberated from these reactions, right? And so that law of conservation of energy is pretty important. We can't ignore that. Energy is neither created nor destroyed. So where did that heat and light energy come from? Well, we say that it came from the bonds between atoms in the reactants. So again, reactants always form products. Reactants, there we go. Reactants form products, wow. And if the reactants have more energy than the products, then that energy has to go somewhere, and that energy will get liberated. And we call those types of reactions exothermic reactions. So this is an example of an exothermic reaction. Exo meaning to exit, therm meaning heat, exothermic reaction. Heat is leaving this chemical system that was comprised of these atoms and the bonds between them. So let's kind of break this down, this diagram over a little bit. When we're talking about energy, we're really talking about chemical potential energy. There's all sorts of other forms of energy. In this case, we were talking about the energy that is formed in the stashed in the bonds between atoms. And so the energy of a reaction we can kind of chart that over time on a graph like this. And we're hand waving a little bit here because I think it's kind of easy to see that there's like, energy in the bonds of like carbon and oxygen and those reactants, and then there's energy in the bonds of products, right? But really, for a reaction to take place, bonds have to be broken, new bonds have to be formed. You're doing this every time you do a model kit lab where you're breaking bonds and forming new ones. So there's all these kind of like intermediates that can form. And those intermediates are kind of like up here, and we don't really talk about them, but it takes energy to get this whole process started. And that energy is what we call activation energy. Oh, hopefully that's all going to erase. There we go. The energy to make those intermediates happen, and then those intermediates kind of collapse down into products, that's what we call activation energy. And so, I mean, one kind of intuitive example of that is like striking a match. So getting whatever's on the end of the match head, like the phosphorus compound or whatever, to react with the oxygen that's in the air takes a little bit of energy, to like that frictional energy to get those molecules to slam together, start breaking bonds, start making new bonds, and then getting the wood of the match, the hydrocarbons in the wood of the match, to react with oxygen in the air around it and burn the match down. So it takes a little bit of energy to get reactants to start forming products. And then we can track the change in energy, and the way we do that is by delta E. And delta E is the energy of the products minus the energy of the reactants. So kind of the energy that we end up with within that chemical system minus the energy that we started with. And we could do just some really simple numbers here. Let's call this the energy of the products, we'll call that 1, and the energy of the reactants, we'll call that 2, and then this, we'll say that's 3, and that's 4, and we're just using this for illustration purposes. We have much better data than that in real life. But in this case, we're going to have energy of the products is 1 minus the energy of the reactants, which is 2, and that's going to be -1. And the important thing about that is a negative number. All exothermic reactions have a delta E that is a negative number. If delta E is positive, then we would have an endothermic reaction. And we'll talk about those reactions when I get back in class. I think that this is probably enough to think about right now. So exothermic reactions have negative delta E's. What are delta E? It's the energy of the products minus the energy of the reactants. Where is this energy? Energy is stored in the bonds of these molecules. It takes energy to break those bonds, and then energy is either absorbed or released when products are formed. And that is, if it's released, that's what we call an exothermic reaction. So with this in mind, and all this hopefully is sinking in somewhat, this is what you need for number 3. So don't skip number 3 on the homework right now. You might want to pause the video and make sure you have all of that information on your notes right there. But this is just the energetics. We don't talk enough about this, but this is really kind of a big part of what makes chemical reactions take place in the first place. Okay, so if you need to write that down, pause it. I'm moving on to the last part for the end of this video. We're almost done, I promise. Number 5, I don't want you to skip this on your homework anymore. I just want to tell you that we're going to do a lab, like either Wednesday or Friday, and it's going to involve all this stuff that we're talking about. The long and short of all of this information is that we have several different redox tests that we can use to distinguish between primary alcohols, secondary alcohols, aldehydes, which are easily oxidized, and then tertiary alcohols, carboxylic acids, ketones, or aromatics that are not, aromatic aldehydes that are not easily oxidized. You've actually probably done some of these reactions already in first year chemistry. There are these common ones, not common like everybody in the general public knows about, but people in chemistry know about: Tollens reactions, Benedict's reactions, Phalings, or potassium dichromate. The long and short of it is, if a redox reaction is possible, we'll see some sort of color change. We'll see some sort of temperature change. We'll see some sort of indication that a chemical reaction has taken place. If there is not an easily oxidizable reaction, then we will not see that sort of reaction. We won't see a precipitate form. We won't feel a temperature change or measure a temperature change. We won't observe a color change. So this is for number 5. The overall idea is that we have different tests that help us determine whether or not something is easily oxidized, and that way we can distinguish between different unknown substances. Pause the video as needed to upload or to write the upload to write these things down and know that they're going to be ready for you on the test. All right, what do you got? You got homework number 2, finish that up. You got homework number 3, get going with that, finish that up. You got the Great Oxidation Event reading. Good luck, Godspeed, may the odds ever be in your favor and all that good stuff.